prove that any group of order p squared was abelian. Now, we already knew that any g of order p is cyclic. So therefore isomorphic to the group Z mod pz by sending a generator of the cyclic group to 1. And we're going to start to develop methods that allow us to analyze G. What about G of order PQ or P cubed? Slightly more complicated products of primes. So we're going to need, here we know non-abelian groups of these orders, at least of order 6. We have S3 of order 6. And last time I gave you an example of a non-abelian group of order P cubed where you took these matrices over the field of P elements. So there are interesting groups of these orders, and we might want to classify them. And to do that, we're going to need to develop a little bit more machinery internal to finite groups. Now let's proceed with this theorem a little bit. I claim that once we know that any group of order p squared is abelian, there are only two possibilities for it. Only two such groups up to isomorphism. Namely, any group of order p squared is going to be isomorphic to one of two groups. Any group of order p is isomorphic to this group. So there's only one group up to isomorphism of order p. So a group of order p squared, there are two possibilities. The first case is that there is an element G in G of order p squared. I mean, the possible orders for an element in a group of order p squared are 1, p, and p squared. Okay, that's it, because the order has to divide the order of the group. If there's an element of order p squared, then G is isomorphic to Z mod p squared Z by the element that takes G, the isomorphism that takes G to 1 mod p squared, and that takes G to the A to A mod p squared. That's a 1-to-1 onto map, which is an isomorphism of groups. So if you have an element of order p squared, it's a cyclic group and is isomorphic to this cyclic group. And the second possibility is there is no element of order p squared. So every G not equal to the identity has order p. Correct? Then the field Z mod pz acts on the group G by, well, I could say A in this field times an element G in the group is G to the 8th power. And that makes sense because if I multiply by p here, which is 0 in this, G to the p is the identity element. So this, you have to understand that 0 times G is E, the identity element in the group. In fact, it's better if you think of this group, which has no element of order p squared, additively, and therefore G to the A, namely as a plus sign, instead of multiplying elements G times H, you think of it as G plus H. That makes sense because G is abelian, so we can think of G plus H as the same thing as H plus G. So this would just be G plus G plus G plus G A times. And this would just be the identity element we could think of as 0 in the additive group. And consequently, what we get in this case is that the group G is actually a vector space over this field. Namely, it's an abelian group together with an operation of a field on the group. Here's scalar multiplication of the field on the group. And consequently, it's a vector space over Z mod PZ. It has order P squared, so it has dimension 2. So as an abelian group, G is isomorphic to Z mod PZ squared, because that's the two-dimensional vector space over the field of P elements. Every two-dimensional vector space is isomorphic to this one by the choice of a basis. So to make this specific isomorphism, you'd have to find two different elements, G1 and G2 in G, that gave a basis for it as a vector space over Z mod PZ. And you take G1 to the A1, G2 to the A2 to the coordinates A1, A2. So if every element has order P, then you have an action of the field on the group, turning the group into a two-dimensional vector space, and you get this. And that group is not isomorphic to this group because this group has elements of order P squared, whereas in this group everything has order P. This is not a vector space over the field of P elements, because in a vector space over the field of P elements, P times anything is 0. Whereas here you have things where you have to multiply by P squared till you get 0. This, by the way, gives a very interesting construction of a group in general. In general, if n is bigger than or equal to 1, we have the group G, which is Z mod PZ to the n, an n-dimensional vector space over Z mod PZ. This has order P to the n, every element not equal to the identity of order P, just like in this case. And that's such a nice group that it has a name for it, just like the cyclic group has a name for it. This is called an elementary abelian group. Elementary abelian P group. It's sort of the opposite kind of abelian P group than a cyclic group in that the elements have as small order as possible, P. Whereas the contrast in this case would be a cyclic group of order P to the n. And in order P squared, there are only two possibilities, cyclic or this. Okay. Now, to go on to groups of more complicated order, we have to actually develop some general theorems. It's enough to do, we're able to do groups of order P and P squared with our bare hands. Now we have to develop some general theorems. And the general theorems we're going to develop were discovered at the end of the 19th century by a Norwegian mathematician whose name is Seelof. And we're going to prove now, or are going to start the proof of what's called the Seelof theorems today. And we'll probably get through the proof today. It's a serious argument. And we'll start doing applications of the proof to groups of order PQ, etc. On Wednesday. I should point out that I'm out of town on Friday. I have to go to the West Coast to raise unimaginably large sums of money from movie moguls for Harvard College. So, and Peter Green is out the rest of this week, too, because he's going down to Princeton to participate in a conference on a major mathematical problem to which he's making fundamental contributions. But on Friday, you're lucky that my colleague Richard Taylor, who was one of the people involved in the proof of Fermat's last theorem, a great number theorist, is going to come to lecture to you. And then Peter will sub for me on Monday as I'm recovering from my various travels. I'll be back on Wednesday, but I'll talk about applications of this on Wednesday. So recall, yes?
Sorry, before you go on, I'm just I might lose the point over here.
Okay, this is just an example. So that generalizes the example I did in order P squared. If you want to know a nice way of going from vector spaces to groups, and you take the vector space of dimension n over the field of P elements, that gives you, in particular, an abelian group. Because a vector space has underlying it an abelian group. But it's a finite abelian group. It has order P to the n, the P to the n choices for these coordinates. Every element in the group has order P, because when you think about how you add things in this group, if you add anything to itself P times, you get to the origin. And we call this, because it's such a nice example, the elementary abelian P group. Okay? Just like we have a name for groups. So we're developing a kind of menagerie of finite groups. We already know the finite cyclic groups. I've just told you about the elementary abelian P groups. We'll even have names for non-abelian groups, as we'll see. The group that I showed you, which was this non-abelian group of order P cubed, given by those matrices with entries in the upper triangular, is called a Heisenberg group, because it's the analog of a group that Heisenberg considered over the real numbers. We'll come back to that. Part of the lore of finite groups is naming everything. Okay, the CELO theorems, we have to discuss the operation of G by conjugation. So remember that G acts on G by conjugation. So this you think of as the set. Namely, it takes an element S to GS G inverse. And the orbits are called conjugacy classes of elements. And the stabilizers, this is like O of S, conjugacy class of the element S. And the stabilizer, G of S, is called the centralizer of S. So that's the set of G such that GS, G inverse, is equal to S, the elements that commute with S. So we've taken a look at this action when we did the class equation. Now, it doesn't just act on G. It acts on subsets. G acts on the set of, or maybe I should say also, because this is a different action, on the set, let's call it H, of all subgroups of G by conjugation. So if I have a subgroup, H, and I want to know what G does to it, it takes it to the subgroup GH G inverse, which is another subgroup. Okay? Yeah? Of all subgroups of G. G acts on its own subgroups. Doesn't necessarily act on subgroups of another group. So here G is acting on its elements by conjugation. You take an arbitrary element in the group to this element in the group. But this doesn't just take elements to elements. If you think about what conjugation does, if you apply it to the elements of a subgroup, so this consists of all things of the form GH G inverse such that H is in H. It's a subset of G, but in fact it's a subgroup. If you multiply two things here, you stay in it. So that gives a way of going from one subgroup to another, and that's a G action. Namely, the identity preserves all subgroups, and it's associative. So we had the notion of G acting on sets. Here it's acting on the set of its own elements. Here it's acting on the set of its own subgroups. Okay? And we want to know what the orbit is. So the orbit of H is the set of subgroups conjugate to H, conjugate meaning of this form. And the stabilizer of H is the set of G such that GH G inverse is equal to H. Now that doesn't mean element by element. That doesn't mean element by element. It means that this set is equal to this set. It could move the elements of H around. So you don't think of that as the centralizer of H. It doesn't centralize everything in H. It just takes the set to itself. So this is what's called, in group theory, the normalizer of H. And I'm going to make two comments about the normalizer of H. So first of all, it's a subgroup because it's the stabilizer of something. The stabilizer of something is always a subgroup. And it's a subgroup that sits between H and G. Because H has the property that it normalizes itself. Moreover, it's a subgroup that sits between H and G, and H is normal in its own normalizer. Clear. If you forget the fact that you're acting by G and you're just acting by elements in the normalizer, they preserve H. And it's the largest subgroup of G containing H in which H is normal. I mean, if H is a normal subgroup of G, its stabilizer is the entire group under this action. Right? That's what it means to be normal in G, that this subgroup is equal to H for all G. It's certainly equal to H for all H. So you see what you can add to H that preserves H in this conjugation business, and it's the largest subgroup of G that normalizes H. So I'll give you two examples of normalizers. It's an important concept. In the group S3, if we took a look at the subgroup A3, the alternating group, which is the identity, the permutation 1, 2, 3 in our new notation, and the permutation 1, 3, 2, namely the elements of order 3 and the identity, that's a normal subgroup of S3. It's the only subgroup of order 3. So the normalizer of this group is A3. Normalizer of A3 is equal to S3. However, if you took instead the group E1, 2 of order 2 inside of S3, and you asked what elements normalize this, well, if they normalize this, they would have to take this element to itself, because there's no other element of order 2 in the group. You see, here you can normalize this by permuting these two elements. That would be okay. And in fact, when you conjugate this group by this element, you'll see it permutes those two elements. So it doesn't centralize it, but it normalizes it. Here, if you have a group of order 2 and you have something that normalizes it, it has to centralize it. And if you calculate what elements commute with this element, there are no other elements but this element. And so in this case, one finds the normalizer of H is just H. So those are the two extremes. You can have nothing else preserving the group, subgroup, or you can have the entire group, or you can have things in between. If you want an example of something in between, and this is also an important special example, if you take the subgroup H inside of 2 by 2 matrices that looks like this, A, B, like this, inside of G, which is GL2 over a field, any field, you'll find that the normalizer of H are the set of matrices that look like this. So there's a case where the normalizer is larger, but is not all of G. Okay? So this language is important when you state the CELO theorems, to have a notion of G acting on its set of subgroups by conjugation. We've already seen the set of subgroups conjugate to a given one is important in the notion of group actions on a set. Because if G acts on a set, and we know the stabilizer of S, that is conjugate to the stabilizer, acts transitively on S, then the stabilizer of S is conjugate to the stabilizer of another point, and the different stabilizers form a conjugacy class of subgroups. So we've already seen these kind of orbits already, but we have to have a name for the notion of the stabilizer. As I say, remember that it does not preserve the points of H pointwise. It just takes this set into this set. Okay. Now let's state the CELO theorems. I need a blackboard for that. So they're generally broken up into 3 parts, although when Celoff discovered them, they were kind of mishmashed. Theorem. Celoff. Assume G is a finite group of order n, which is factored as p to the m times n, some power of a prime p times a number where n is prime to p. So that this is the highest power of P that divides the order of the group. Okay. Then, 1. There is a subgroup H of G of order P to the M. Namely, we have a possible order for a subgroup because this divides the order of the group. In fact, you can always find a subgroup which has order the highest power of P dividing the order of the group. Okay? 2. These subgroups, by the way, of order P to the M are called C-law P subgroups. Sometimes you omit the P if you know what prime you're talking about, just a C-law subgroup. 2. If K is a subgroup of order P to the A, any A, we know A is less than or equal to M because the order of a subgroup has to divide the order of a group. Then K is contained in a conjugate of H, the C-law P subgroup that we found up there. So as a particular case of 2, in particular, any 2 P C-law subgroups H and H prime are conjugate. Because, take the case where K has order P to the M, so is a C-law P subgroup. Then, the fact that K is contained in a conjugate of H, well, the conjugates of H have the same order, and if you have two groups of the same order, one contained in the other, they're equal. So that would say that K is a conjugate of H. So there are subgroups of this order. Any 2 of them are conjugate. Conversely, any conjugate of H is a C-law P subgroup because it has the same order. So the C-law P subgroups form a single conjugacy class. That's an important thing to know. You can't have any better than that. And finally, the third part of the C-law theorem gives you an estimate of how many C-law P groups are in that conjugacy class. 3. The number well, let's give that number, a name. I was going to call it S for C-law, but I better use something else. The number L of C-law P subgroups of G in this single conjugacy. Divides M, the number here divides N, the number that's left over, divides N and satisfies L congruent to 1 mod P. Leaves a remainder of 1 after dividing by P. So there's a restriction on the number of CP. There is always a C-law P. Any 2 of them are First of all, even the first part of this theorem is remarkable. It's absolutely remarkable. If you take groups of order 12, it's not necessarily true, so let's make that remark so that we start to appreciate this before we prove it. Note, if D divides the order N of G, there need not be a subgroup of order D. And an example, if you take G to be the alternating group on 4 letters, has order 12, but it has no subgroup of order 6. Okay? So this is now notice that this is not the power of a prime. What the C-law theorems would tell us is there exists an H of order 3, a C-law 3 subgroup, and there would be an H prime of order 4. Those things are forced by the C-law theorem. But this is PQ. C-law theorem says nothing about that. So sometimes this is called a local theorem in group theory. Local because it's localized at one prime. You only focus in on one prime. Okay, let's start the proof. So there are many, many proofs known. Many, many proofs. I think there now must be 20 or 30 proofs of this theorem that have been discovered. And I like the one in Artin very much. I'm going to imitate it. I'll probably try to give you some others later. So Artin is basing it on the following fact. That if you take the order of G and you take the binomial coefficient n, choose p to the n. N is this number, p to the m, I keep using my notation wrong. P to the m is prime to p. That's the fact we're going to use from outside of group theory. So why is that? Well, write down this binomial coefficient. It looks like this. n minus 1, n minus 2, down to n minus p to the m plus 1 divided by p to the m minus 1 down to 1. Okay? If you take a look at this term, now we're just going to see the power of p dividing the numerator and the power of p dividing the denominator are the same. That's how we're going to, this happens to be an integer. And the way we're going to prove it's prime to p is we're going to calculate the power of p dividing the numerator, the power of p dividing the denominator, and we'll show the same. So that's a nice thing you can do about fractions. It's based on uniqueness of prime factorization. Well, the power of p dividing n is p to the m. So we have the same power of p here. What's the power of p dividing n minus 1? 0. It has to be 0 because this is divisible by p, and p is bigger than 2. That's exactly the power of p dividing this term. Now, what's the power of p dividing n minus 2? Well, that depends. P might be 2, right? And if p is 2, you have 1 power of p dividing this. And you have 1 power of p dividing this. So in general, this is called, by the way, the order of p of whatever. The power of p dividing n minus k is equal to the power of p dividing p to the m minus k. And I'll let you check that out. These k's, by the way, are all less than p to the m. So in particular, the power of p dividing k is less than or equal to m minus 1. So this, whatever this order is, it's easily calculated by the power of p dividing k, and that's exactly the same as the order here. So in each term, you get a matching of the powers of p dividing the terms, right down to here where this is not divisible by p, neither is this. And so when you add them up, the power of p in the numerator is the same as the power of p in the denominator. And when you calculate this number, it's not divisible by p. Okay. Now that's the key to the proof. Because what we do is we have the group act on a set which has this size. Let G act on the set, this is a weird set, S, of all subsets of G which have order p to the m. We're trying to prove there's a subgroup of this order, but we don't know that. We can certainly find subsets of that order, right? Because this order is less than or equal to n. And the number of subsets of that order is this binomial coefficient. So we've just shown that the number of elements in S is prime to p. Okay. Now we're going to get our CELO subgroup as the stabilizer of something in that set. As a stabilizer, GS, for this action. And that's one way of getting subgroups out of actions on sets. Anything that stabilizes the point is a subgroup. Right? So the thing we're acting on are not subgroups, but we're going to see that one of these sets is stabilized by a group H of order p to the m. Okay. Why? Well, we use our usual orbit method to break this action into orbits. Which tells us that the number of elements in S is equal to the number of elements in the first orbit plus the number of elements in the second orbit plus the number of elements in the nth orbit. And on each orbit, the group acts transitively. So in the first orbit has size the order of g divided by the stabilizer of S1. And the second orbit has size the order of g divided by the stabilizer of S2, down to the order of g divided by the stabilizer of Sn. So that we've been doing in general for group actions on sets. It's a finite set. We break it into orbits. On each orbit, the group acts transitively, so the size of the orbit is g modulo the stabilizer, because the transitive action is modeled on the action of cosets of the stabilizer. Okay. This has order prime to p. If every one of these orbits had size divisible by p, there's no way you could add them all up and get some number prime to p. Correct? So the conclusion is that one orbit has order prime to p. There is at least one orbit of order prime to p. Correct? Okay, let's call that the orbit of S1. Say size of OS1 is prime to p by reordering. Or let's just call it OS. S is one of these SIs. Okay. Now, we see what that says about the stabilizer. Since the order of OS is equal to the order of g, p to the m times n, divided by the order of gs, is prime to p, we must have this power of p dividing the order of the stabilizer. Okay? Because if you have a number expressed as an integer over an integer and it's prime to p, the power of p dividing the denominator must equal the power of p dividing the numerator. Same argument we did for the binomial coefficient. So p to the m divides the order of the stabilizer. So this is beginning to look good. If we could just show that it wasn't any larger than p to the m, then we'd have our CELO subgroup. But I claim and this is the key thing, that the stabilizer has order less okay, we're going to see that in a second. I should have said, by the way, Oh my God. I didn't even tell you how G acted on the sets. I said let it act on the sets, but I didn't tell you how it acted. So, no, I don't want it to do that. I want it to act on the sets by translation. Sorry. By translation. So if I have a set, if I have a subset of G, which I better not call H, I'll call it J in G, goes to GJ in G. By left translation. So this set has the same size as this set. Yeah?
Just to be sure, you're using the pound sign and the absolute
In the same way. Interchangeably, I'm sorry. So this also means the order of GS. I should be more systematic, and if I were Bourbaki, I would have chosen one and used that one, but I'm using them interchangeably. Good point. Good point. So let's go over the action on the set is like it acts on points of the group by left translation, not by conjugation. So it takes a set J to this set J, and so the rest of this argument didn't depend on what the action was. Made no reference to the action, just used the fact that the number of things it's acting on is prime to p, therefore there has to be some orbit of order prime to p, therefore there has to be some stabilizer divisible by that. But now I'm going to claim, using the action, that the order of GS is less than or equal to p to the m. In fact, I claim, in fact, the orbit of S is a union of, let's see how I want to say this. I always get confused at this point. Yes. This S is a subset J. So S corresponds to some subset J in G. And I have an element of the stabilizer of that subset. So let's write, so if G is in GS, then GJ, well, it's equal to J. I mean, it has to be a set of the same size, so it's equal to J. It's contained in J. And then I claim that this implies that J is a union of left cosets of GS. For the stabilizer, in particular, the order of J, the size of J, which we know is p to the m, is a sum of the order of GS a number of times. In particular, the order of GS is less than or equal to the order of J, the size of the subset. I claim that if you have an element in the stabilizer, you have this, and that forces J to be a union of cosets for GS. Because if you think of the action of G on, here are the cosets of GS. If you have one element in J, then you have all the elements in that coset in J. Right? Let's see if I've got it the right way. GJ, GS. Yeah, if I have an element in one of these cosets, suppose I have an element in this coset, J, then I claim that I have all of GS in J, because G stabilizes that by left multiplication. So I stay in that coset, and I can get anything in that coset from anything else in that coset by translation by GS. Likewise, if my element J contains some element in another coset, then by the fact that G stabilizes that, I can get anything in that coset by translating by GS. And consequently, the only stable subsets I can make under this GS are a union of these left cosets, and consequently the order of J has to be bigger than the order of GS, because the order of GS is the size of one of the cosets. And that's the end of the proof. The first is that p to the m divides this order, but on the other hand, the stabilizer of a subset has order less than or equal to p to the m. And in fact, you'll find that a subset has stabilizer of order exactly p to the m if and only if it's a CeLo p subgroup. And that's the end of the argument, although you don't need it. In fact, J has stabilizer of order p to the s if and only if J is equal to H is a CeLo p. In which case, J is equal to GS is equal to H. So the only subsets that have a stabilizer of this order, and we have to have one subset whose stabilizer is divisible by this, are the subgroups which are CeLo p subgroups. And that's the proof of the existence of a subgroup of order p to the m. So again, this is a fairly complicated argument. You've got to go through it yourself slowly. A divisibility argument shows that you have to have some stabilizer divisible by this number, but any stabilizer has order less than or equal to that number. Therefore, there has to be some stabilizer of order equal to that number, and that happens to be your CeLo p subgroup. Okay. That's the easy part of the theorem. Now, let's prove part 2. All right, now this is quite cute. Suppose I take my CeLo subgroup. H is my CeLo subgroup found by 1. This is part 2. And I choose, and I have the group action G acts transitively on the coset space of H, which has order n prime to p. So before I knew the existence of a CeLo p subgroup, I had to work quite hard to find an action of the group on a set of order prime to p, on the set of all subsets of order p to the n. But here, I have a natural transitive action on a set of order prime to p. Okay, the stabilizers of any point S in S, G sub S, are the conjugates of H, right? Because it's a transitive action. H is the element that stabilizes the identity coset. The other cosets are stabilized by conjugates. So G sub S would be the coset maybe SH, and it would be the conjugate SH S inverse. G sub S would be this. If it acted on, the stabilizer of that coset would be this conjugate. So that's also a p CeLo subgroup. And we get all the conjugates of p CeLo subgroups by taking the stabilizers of points in this action. Okay, now let's see why any p group is contained in one of these. Let K, sure, I'll stop. So we're going to try to prove that this, by the way, these things are called p groups, groups of order p to the a. So we found one CeLo group. I claim that its conjugates are the stabilizers of other points in this set for the left action. If you want to stabilize this coset, you get this conjugate, and any conjugate comes from such a stabilizer. And now I'm going to start with another p group, another p subgroup, and have K act by the restriction of the G action on S. Namely, have K act on the cosets of H by left translation. Just restrict the G action to K. That makes sense. Okay? Again, since this order of the set is order prime to P, there must be an orbit say the orbit of SH of order prime to p. Because if all the orbits had size divisible by p, the entire set would have size divisible by p, but it doesn't. So there must be an orbit, say this orbit, of order prime to p, which means that its stabilizer, so the size of the orbit's prime to p, so the order of k divided by the order of the stabilizer is prime to p. The order of k is a power of p. So that means that the order of the stabilizer has to be equal to the order of k. So there must be an orbit fixed by k. But the order of k is p to the a. So we must have the order of the stabilizer of that orbit is equal to the order of k. What is the stabilizer of this orbit in k? That's just the group k intersect g sub s. It's the elements in the stabilizer in g which lie in k. Correct? G sub s we saw was a conjugate of h. So the order of this group has to be the order of this group, and the only way that that can happen is if this group is contained in this group. If k isn't totally contained in this group, then when you intersect it with this subgroup, you're going to get something strictly smaller than k. But the order of this is the order of k. That shows that our p group that we started with had to be contained in some conjugate of our CeLO p subgroup, and in particular that if we started with a CeLO p subgroup, it was actually conjugate. Now this is very indirect. Let's see why it's so indirect. We don't know which conjugate of h contains k, because we don't know which orbit here has order prime to p. We just know there has to be one of them. And you can't actually find it by this method. It's just an existence proof. That's one of the problems of the CeLO theorems. They're not that constructive. Finally, let me try to do 3. We may not have enough time, but I'll start this again on Wednesday. Take a look through these proofs. They're exceedingly clever counting arguments. No one would suggest that one should just sit down and do these for homework. 3. Okay. I think we can find it. Now, the number of CeLO subgroups, which we called L, is, I claim, the order of G divided by the order of the normalizer of a CeLO subgroup. Of a CeLO P. Because, as G acts transitively on the set of CeLO P's by conjugation. That's part 2. And the stabilizer of H is what we call the normalizer of H under the conjugacy action. So the number of CeLOs is the order of G divided by the stabilizer of a point in that action. That's the normalizer. Whatever the normalizer it is, it contains H. Right? So the order of the normalizer is at least p to the m, and therefore the number of them divides what's left, n. That's the first part, that the number divides n. Since H is contained in the normalizer of H, normalizer of H has order divisible by p to the n, So L divides what's left, which is m. N, little n, I'm sorry, which is capital N divided by p to the m. That's the divisibility statement. Now we have to prove the congruence statement. Again, this is going to be one of these setting up a G-orbit problem. Now, consider the action of, we know the group acts transitively by conjugation. Restrict the action of conjugation on the silos to the subgroup H itself. So we have a set of L silos, and now we just let the subgroup H act by conjugation. I claim there's an orbit with one element. Has one element. All other orbits have p to the a elements with a greater than or equal to 1. That's the claim. If that's the case, then the total number in the set, L, is congruent to 1 mod p, because it's 1, the number of orbits in the set H, plus p times other things. Okay? Why do all other orbits have p to the a elements? Well, they have some power of p elements because it's an orbit of H, which has order p to the m. And so the size of any orbit divides this. So it has to be some power of p. You just have to show it can't be 1. So suppose there was another CeLO P that was stable under conjugation by H. If H prime were in an orbit of size 1, then H normalizes H prime. Right? That just says that under conjugation by H, H prime is stable. So H normalizes H prime. So H and H prime are two subgroups of the normalizer of H prime. Now this is a killer. Are you ready? Watch this. This is a subgroup of G. So its order is some power of p. In fact, it has to be p to the m times some n prime. Maybe some n prime. But in particular, this power of p is the same power of p that divided the order of G. It has to be there because it's in these two things. Therefore, these two things are CeLO P subgroups of this. Correct? We forget about G now. They're now both CeLO Ps of this. And we can apply the CeLO theorems to any finite group. So now we apply it to this group. And part 2, which we've proved already, says that they're conjugate in that group. So conjugate in the normalizer of H prime. But in the normalizer of H prime, the only thing conjugate to H prime is H. If you look at the action of conjugation on H prime inside of this group, it doesn't move it at all. So H prime is equal to H. And that shows there's only one orbit of size 1. It's a totally cool killer argument because you leave the group G. And you just apply the CeLO theorems to a subgroup, the parts that you've proved, 1 and 2. So take a look at this amazing argument. We'll come back and review it a little Wednesday, and then I'm going to give you some examples to show you how you classify groups of order PQ.